Okay, welcome class. We're going to do some further work on some important differentiation and integration techniques that you may need for the exam. Now, it's looking at implicit differentiation as one of them. Okay, you may have looked at a few problems involving that already. We're going to clarify some of the ideas. And we're going to look at a process where we have some parametric equations, and we're going to see how differentiation might be applied with them. Then we're going to examine this thing called Euler's method, and it's for approximating values of the solutions to differential equations. So let's get to it. Okay, so implicit differentiation, it involves a technique to determine different derivatives of an implicit equation. And an implicit equation is when we have the x and y's together on one side of the equal sign in a relation, just like that. That's called an implicit equation, because there is no way at how it can be expressed in terms of y in an explicit way. And we can, such relations like this are used to model ellipses and hyperbolas and circles and different curves like that. And so when we differentiate these types of relations, we're going to draw on a couple of skills. One is being able to differentiate using the product rule and differentiate using the chain rule. But we're going to consider the chain rule in a specific form. It's where we have some function of y, and then when we differentiate with respect to x, we realize we can't do that because we've got a function of y, there's no x's there. So first, the first part of the chain rule, this term, is let's go ahead and differentiate with respect to y anyhow, but we have to balance that out and multiply by the dy dx, okay? Just so it's equivalent. And we're also going to use some derivative notation, y dash, just to make it a little bit more simple. We might already be used to differentiating functions like this, df of x dx. Now, when we're differentiating these implicit equations, there's some approach we have to follow. You've got to think about it. We're differentiating in two parts. We're going to differentiate the left-hand side of the equation first, as a separate job to differentiating the right-hand side of the equation. Okay? So we consider it in this form. If we differentiate the whole lot altogether, it's the same as the left-hand side derivative is equal to the right-hand side derivative. Okay? So let's break this down into a few parts now. We'll reveal all that step by step. So consider some equation here that has x's on both sides, x terms on both sides. This is not an implicit equation, but we're just going to practice the idea of differentiating as an operation to both the left and the right hand side of the equation. Okay? So derivative of the whole lot becomes derivative of the left and the derivative of the right. So that gives us 8x minus 3 is equal to 5. Okay? Nice simple exercise. What about this one? Derivative of an equation like that, x squared minus x times e to the 2x equal to cos of 3x. Then derivative of left and derivative of the right, and it gives you that. Okay? Now, do we notice something, a specific approach we did there? What kind of technique did we do to differentiate that left-hand side expression? That was, in fact, a product rule was used. Okay? So we have to be mindful that we're going to be drawing on those techniques quite regularly, in fact. What about this type of expression? Then when we're doing the derivative, what kind of technique do you think we'll need to employ for this one? one or two types of techniques. We will end up with that as the derivative. And what did we do to achieve that? Well, we used both product rule and a chain rule together. Okay? Now, what happens if we take the derivative of such an expression? Okay, x times y equals 1. Yeah? How are we going to handle x and y's in the same expression? Well, if you remember a little bit from class, first we're going to differentiate both sides, and then we see, well, the derivative of the right-hand side, well, that's going to be nice and straightforward. Derivative of a constant is always 0. But we have to recognize that the x times y is a product. And we're going to use the product rule in differentiating. Okay? And from that expression, we are also going to make it a little bit more simpler for ourselves. And this dy dx here, we're going to write in a simple notation and use y dash instead. So we'll get that as our expression. Okay? Now, from that, we haven't fully found the derivative. Because what is a derivative? What function do we use to represent the derivative? Well, that is dy dx. Okay? That is the derivative. That's what we're after. We're after an expression for y dash. So, our job is now to transpose. We have to transpose what we have there for y dash. Okay? Must transpose, and we'll end up with that as an expression. Okay? Does that make sense? So, if we're interested in to express y dash fully in terms of just x, and not also another y term, because that's what we've ended up there, some function of y and x. If we want to get rid of that y and just have x's, then we substitute. We're going to have to bring in a substitution approach now. So you can see from the original rule at the start, x times y is equal to 1. Then I can transpose that a little bit, rearrange it. Y will equal to 1 on x, and I can substitute that in, and I'll get my final expression. Y dash is equal to negative 1 on x squared for the derivative. Okay? So now, next step is looking at what happens when we differentiate functions of y. This is when the chain rule comes in. Okay? So our df of y dx, trying to differentiate with respect to x doesn't work, so we have to use the chain rule. First differentiate with respect to y, then multiply by that dy dx. We're going to use a y dash instead. Okay, so that is done in a simple way like that. Okay, so it's a little thing to remember. You can say, well, when we've got a term with a y in it, and if we differentiate with respect to y, then we just multiply by y dash at the end. So let's look at an example. There we have, so there's our implicit equation in terms of x's and y's. First step is differentiate both sides with dy dx on both sides. Okay. Now, the next step is using the product rule. We're going to differentiate each term. So derivative of the left, the derivative of the right. We have the first part, okay, the yellow here. When we differentiate those two terms, we can see first they're a product of terms. X squared to multiply by y to the power of 3, we have to use our product rule. So we'll have 2x times y to the power of 3, that's the u dash times v plus, and then the last bit is u dot v dash. Product rule application there, understand? Now, this here is where the chain rule kicked in. is when we differentiate the y to the power of 3 with respect to x, first with respect to y that becomes 3y squared, and then we multiply by dy at the end, okay? And we have a similar kind of process for differentiating the next term, the blue section, okay? Product rule, and when we get to differentiating the y squared with respect to x, first do it with respect to y and then multiply by y dash at the end, okay? And keep in mind, we also must do the same thing to the right hand side also. So this 6y becomes 6y dash. Okay, the derivative of y with respect to x is just y dash. Okay, so that's how we're going to do it in full, find it, the full derivative. Now the job is, we want to transpose for y dash. What is the derivative itself as a rule? So collect all your terms. This is a y dash term, that's a y dash term, that's a y dash term. Collect all your y dash terms, and then factorize that y dash out as a common factor. Bring every other term that it does not have a y dash in it, add it or subtract it to the other side of the equation, and that's what we've got there. Okay, and then finally divide that whole bracket down to the right hand side, and we get our beautiful expression. Okay, the next technique we're examining is when we're finding derivatives of parametric equations. So parametric equations has this extra variable in it, t. So we might have two equations, one equation for x, one equation for y, in terms of t. So we might be interested in, well, what's the derivative, dy dx, of these, what curve does it make, these parametric equations, and what is the derivative of that curve at different points? We're going to be drawing on the chain rule as we do it, such that if we've got equations in terms of x, we have to introduce equations in terms of t, we have to be introducing the t variable into our derivative somehow. So we can write our chain rule in that manner, and then the dy dx can be expressed like that. The derivative of the y as a function of t rule multiplied by the reciprocal of the derivative of x as a function of t rule. Okay, so parametric equations are useful for producing ellipses, for instance, and circles and other things like that. So let's look at an example of the ellipse. So here are the two parametric equations that would produce an ellipse of this type. And so we might be interested to know, well, there's our tangent to the curve at some point, x equals 2, for instance. Well, the derivative of the function at a point relates to how steep that tangent is. Rise over under the tangent. What would be the gradient of the tangent to an ellipse at a certain point? That could be what we might be after. So let's consider the derivatives of this parametric equations that produced our ellipse in terms of t first. So step 1, differentiate with respect to t. So the first one, dx dt, derivative of cos becomes a minus sign. And the 2 in multiplying the t becomes a multiplying factor at the front. 2 times 2 gives you your 4. And if we keep going and differentiate y with respect to t, we'll get a function like that. So putting those two rules together now, using our chain rule and expressing that in terms of t, we will have this expression. Okay? And so I can simplify this expression where cos over sine becomes a cot function. Okay? And now we've got our function of t that represents the derivative of the curve, dy dx. Now, this could be used if you want to know the gradient of the tangent at a particular point. such is there. What is going to be that gradient value? We need to know what a value for t is in order to substitute it into the derivative rule and evaluate the dy dx. Now let's consider this as an exam problem. Here's your curve, parametric equations, and let's find dy dx at some point. Okay? Now this is, first off, it's important to recognize, well, that's not a t value there. It's not, that's a x and y coordinate. That is some point on the curve produced by this pair of parametric equations. So let's consider first taking the derivative of each parametric equation with respect to t. So there's the first one. And dy dt becomes a negative sign. And so I'm going to put them together using my chain rule. And I will obtain that, a sine over cos expression, which is tan. So I get negative half tan of t. Okay, now I still don't have enough information because I don't know what my corresponding t number is for this given x and this given y, where x is 1 and y is root 3 plus 3. So I'm going to have to determine it. This is only in terms of t, and we have an xy coordinate given, so we have to get the corresponding t value for this given xy. So I'm going to substitute x equals 1 into my expression for x at the very top, this one, and I'm going to go ahead and solve for t. I'll have sine of t is a half, and by solving that little circular function equation, I will get pi on 6. Now, fortunately, this pi on 6 is in the first quadrant angle only. Why should I only be considering a first quadrant angle and not another one? Well, look at the point here. This is, if you consider it on a small unit circle, you have a positive x value. So in the first quadrant there's positive x, and you've also got a positive y value. Okay, positive x, positive y, that only occurs in the first quadrant. So it has to be a first quadrant angle only. Okay, so I'm going to take my t value that I've just worked out, pi on 6, and let's substitute our t value, t equals pi on 6 into dy dx. So now I'm thinking about tan of pi on 6. Well, that is root 3 on 3. That's right. And I multiply by negative a half and I get this numerical value. So therefore, dy dx is negative root 3 on 6 at that point, at that x and y coordinate. Okay, now we could also approach this slightly differently. We could think about it as, well, let's first work out what's the Cartesian equation for these two parametric rules. So I rearrange x, my sine and my x rule and my y rule in terms of sine and cos, and now I'm going to use my trig identity, combine them together to get the parametric equation for the ellipse. Okay? Now, from that, I could say, well, how about if I expand all the terms and I'll have a relation in terms of x and y, and then I could use implicit differentiation like we have just looked at to differentiate this expression and then transpose and solve for dy dx. But it may be a more difficult approach to do it in that manner. So this is where the power of our chain rule approach comes into play. the last thing we're going to be looking at is Euler's method for approximating solutions to differential equations. Now, this draws on the linear approximation rule for a y value, okay? And our job is to apply it to differential equations. We're interested in, well, what's the y values of a particular solution to a dE that's given to us? So there's your linear approximation rule. Now, for a given differential equation, it might be of this form. Some derivative that's given to us as a function of x could also be a function of y, okay? And an example is our dy dx is equal to 2x, and we're told that at x equals 0, y is equal to 1. That's like our initial condition. So if I go ahead and solve this differential equation, I will get this as a solution. Okay, and you can check that yourself going through the steps, and it has a nice graph here. Being exponential equation. Alright. Now, from that, we might be interested in saying, well, what is the y value we will get, okay, for a given x value? So, this is the information given to us. How did we obtain this? Y is approximately 5.01 at this x value. Well, I can apply my Euler approximation rule to do it. So it works like this. We have to break it down into its parts. So first off, let's identify whenever we use a function of x, that is the right-hand side of the dy dx. Okay, it's the derivative that's given to us. Then the x of n plus 1 equals x of n plus h. This is the way we work out all our x numbers. And the corresponding y numbers are given by this rule. Now, why do we do it in this way? You have x numbers and y numbers. Well, we approach this method as like taking steps. A little bit step to the left and a little bit of a step up. Okay? This process is called what's called an iterative procedure. Okay? It means we do a rule to get one value, we plug it into another rule and we get another value, we take that rule and put it back in the rule. We have to do things step by step at a time in order to obtain the value we want. Okay, so let's estimate the value of y2 for a step size. H is 0.1. Now, from that information, this is my goal for that step size, and I've told this part here. This is giving me the initial condition, tells me the values of x and y at the very beginning. So from that, I need to identify that my first x value is going to be 0, and with a corresponding y value of 1. That's my first step. Okay? So then, the next step in x, the next value of x, will be the first value of an x plus the step size. Okay? 0 plus 0.1. Alright, so x1 has that value. To find the corresponding y1 value for that x1 value, I will have y1 is equal to, using the rule, y0 plus h of f at x0. Okay, where, remember, our f of x is given by the derivative, dy dx. That's our e to the 2x. So y0 is 1 plus 0.1 of e to the 2 times 0. Now e to the 0 gives you a value of 1, so I'll have 1 plus 0.1 gives me 1.1. Okay, very good. So I've worked out what x1 is and what y1 is. Now I'm going to take that information and use it again to work out the next step. But before we do that, I'm going to put it together on my plot here. So when I've worked out x naught, well, we have x naught and y naught. So when x is 0, y is 1, that's that point. 0 and 1. Now I've worked out x1 and y1. So if I take one step across, going across this way, that's my step size, my h, and then I get to up a little bit to get my y value. There's another point. So that is x1, y1 when x is 0.1, y is 1.1. Okay? Alright, let's work out y2. First let's get x2. x2 is x1 plus h, the step size. Okay, so that is x1 is 0.1 plus 0.1, 0.2. Now, what was the corresponding y value for that point? Let's work out y2. It's y1 plus h times f of x1. So y1 we worked out previously, 1.1. I take that value, I put into the rule. 0.1 of, now e to the power of 2 times x, which is my x1 value from previously at 0.1. Okay, so now